So, dear students, welcome to the last lecture of the subject, which will finish with random processes in continuous time, and I will show you in the end some applications and some generalizations of this topic, so you can see that everything what we theoretical study during the semester has its practical applications. So, random processes with continuous time is the topic for today. And I will start with the same type of the processes as we studied last week. And these processes were called Markov processes. We start with Markov chains, which means that we will consider discrete states of the process, and the definition is the following. Markov chain with continuous time is the random process xt, where t is from some index set t, which is a subset. In fact, we can write that it is an interval from A to B, where the interval can be either open or closed, or half open, half closed, not important. Which is a subset of real numbers. Satisfying the Markov property. And the property is that the probability that in the time s plus t, we will be in the value in the state j, conditionally on being in the state I in the time s, Sn, Im, it is the best notation. So the property, the probability that in some future time s plus t, we will be in the state j, conditionally on being in the state I in the time s, which is usually the present time, and being in some other states in previous times, is equal to the probability that we will be in the state j, conditionally on we are in the state I, and we can forget everything what happened before. And there must be, of course, the condition that the probability of everything what is in the condition as positive probability. In order, we can define the conditional probability. So, for all t and for all states that's it. So this is the Markov property as mentioned last week, meaning that the future values depend only on the last known value, but not on the past. That's the Markov property saying by words. And similarly, as last week, when we considered discrete times, so here we have the time n+1, here we have the time n -1, and so on and so on, we supposed that everything depends only on the one step and not on the concrete time n. We will suppose the same here. So we will suppose that if this probability doesn't depend on S, or better say, this probability doesn't depend on S, but only on the difference T, we call the Markov chain to be homogeneous and we denote this probability which doesn't depend on S but only on T as P ij T. Great. And the same what we did last week, we will do this week. Here we have some elements P, I, J. Now they depend on T. Last week it was the probability of getting from the state I to the state J in one step. Now it is the probability of getting from I to J in time T. So also the metrics of these so-called transit probabilities will be a matrix depending on T. So we will construct the matrix P depending on T. Or in fact, we will construct the system of matrices with the parameter T. But I think that the first name sounds better. Okay, so let's consider one example for which we will construct this matrix of transit probabilities. We will again consider the building with some bulbs, and we know that in this building, so in an arbitrary building, the average number of bulbs, light bulbs, which are broken per 1 week is 2. The bulbs are put aside, the broken bulbs are put aside to a box with 3 sectors, let's say, or sectors, yeah? So we have a box and 3 bulbs can be put to this box. And we want to construct the matrix of transit probabilities for the Markov chain xt with positive time t, where xt, okay, it's better to write xs because t is the difference of times. xs describes the number of bulbs in the box in the time s. So, what we know? We know that the average number of bulbs which are broken per week is equal to 2. So, let's denote x the number of broken bulbs in t weeks. So we'll consider the time in weeks, and of course the number of weeks is not discrete, it is continuous time, and so t can be an arbitrary positive real number. And the number of bulbs in t weeks is the number of independent events, so it has Poisson distribution, and the parameter is equal to 2t. And because we know that when t is equal to 1, when we consider 1 week, then the average number of broken bulbs is equal to 2. So when we consider the time t weeks, we must multiply the parameter by t. And for example, in 2 weeks, we broke 4 bulbs in average. In 10 weeks, the number of broken bulbs will be 20, and so on and so on. And it means that the probability that no bulb is broken is equal to 2t powered by 0 over 0 factorial times e powered by minus 2t. The probability that x is equal to 1 is equal to 2t powered by 1 factorial times e powered by minus 2t, and so on and so on. So it is e powered by minus 2t 2t times e powered by minus 2t, and so on. Okay, it is enough for construction of the matrix of transit probabilities. So we consider the bulb, the box with 3 sectors, and it means that either no bulbs is in the box, or 1 bulb, or 2 bulbs, or 3 bulbs. There cannot be more bulbs in the box, and that there cannot be less than 0 bulbs in the box, of course. Yeah, so in fact, our process will have only 4 states: 0, 1, 2, 3. And now, what happens? If there is no bulb in the sector, so we construct the probability that there will be j bulbs in the time t if there are I bulbs now. So if there is no bulb in the box, what is the probability that there will be no bulb in the box in time t? It is the situation that no bulb will break in the time t. So it is equal to the probability that no bulb is broken in this time t. What is the probability that there will be 1 bulb in the box when there is no bulb in the box now? It is the probability that 1 bulb will break. And the probability that 1 bulb will break is 2t times e powered by minus 2t. The probability that 2 bulbs will be broken is 2t powered by 2 over 2 factorial times e powered by minus 2t, which is 4t squared over 2 times e powered by minus 2t, which is 2t squared times e powered by minus 2t. So the probability that there will be 2 bulbs in the box when there is no bulb now is 2t squared times e powered by minus 2t. Okay. And what about 3 bulbs? There will be 3 bulbs in the box when there is no bulb now, in the situation that at least 3 bulbs will be broken. And because if there are more than 3 bulbs broken, for example 4 or 5 or 6, we will have to use a new box. But our process describes the number of bulbs in this box. Yeah? So when more than 3 bulbs is broken, when for example 10 bulbs is broken, then the other bulbs will be given to another box, and we don't care. So here we'll put 1 minus the sum of all these probabilities together. And it makes sense because the sum in each row must be equal to 1. And the process must jump to either 0 or 1 or 2 or 3. So it corresponds to the situation, to the theoretical property of the process that the sum of probabilities in each row must be equal to 1. And that's it. So, or that's it. That's the first row, of course. It's not the whole matrix, but that's the idea of construction of this matrix. So now, let's suppose that there is 1 bulb in the box. It's not possible that there will be no bulb in the box when there is 1 bulb now, because we fill the box. We don't empty the box. So the probability that there will be 0 bulbs when there is 1 bulb already is 0. the probability that there will be one bulb is equal to the probability that no bulbs will break. And the probability is e powered by minus 2t. The probability that there will be two bulbs when there is already one bulb in the box is equal to the probability that one bulb will be broken. So it is 2t e powered by minus 2t. And the probability that there will be three bulbs is, as before, 1 minus all probabilities in the row before, so e powered by minus 2t times 1 plus 2t. And analogously to the previous, if there are two bulbs in the box already, it's not possible that there is 0 bulbs or 1 bulb. It is possible that there will be 2 bulbs, and it corresponds to the probability that no bulbs will be broken. And 1 minus the previous is equal to the probability that there will be 3 bulbs in the box. What about the last line? When there are already 3 bulbs in the box, nothing else will happen. There will be 3 bulbs forever. Not forever, practically, of course, but for our process, it means that forever there will be 3 bulbs. And because we don't empty the box. And it is not possible that there are less than 3 bulbs because the box is already full. And that's the matrix of transit probabilities, which depend on the time t. But we don't care, it's only the parameter. And when we consider some concrete time t, we will put the number instead of t, and that's it. So, that's the matrix of transit probabilities. And now the usage of this matrix. Recall that for Markov process, with discrete time, where the matrix P was the matrix consisting of the elements Pij, where Pij was the probability that in the time n plus 1 will be in the state j, while in the time n we are in the state I. First, the Chapman-Kolmogorov equation held, and the Chapman-Kolmogorov equation was probability that the matrix in n plus m steps, so it means m plus L, because we have n here, so in order it is not confusing. And the probability of transit probabilities, the matrix of transit probabilities in m plus L steps is equal to the matrix of probability in m steps times the matrix of probability in L steps. And these matrices are equal to the mth and lth power of the matrices. So It was Chapman-Kolmogorov equation in the discrete time, and the same equation holds in our case. Which is denoted so that the probability matrix in the time, the matrix of transit probabilities in the time s plus t is equal to the matrix of transit probabilities in s times the matrix of transit probabilities in t. And so it is the same because the idea is the same. Here we have some started time, here we have some time t, here we have some time s, and when we need to get from the state I to the state j in the time t plus s, we first need to get somehow to some state here in the middle in the time t, and then we must go to the state j. Yeah? And we can go through all states. So again, what we use is the sum of products of the transit probabilities from here to here times the probability of transit from here to here. And so it is the same idea. But because we construct the system of matrices for all parameters t, this equation is, from practical point of view, quite useless. Because when we have the matrices for all t, why should we calculate the probability in some sum of times as the product when we directly have this probability matrix in this system? And so just in order, you can see that the same equation holds also for the Markov chains with continuous time. I showed you this equation in continuous time, but from practical point of view, it is not used. The second property I want to recall is that we constructed so-called stationary distribution. The stationary distribution was the distribution, in fact, the vector of probabilities of the process lying in the concrete states in arbitrary time which is far away from the origin. And so it was the vector of probabilities for which okay, it must be transpose it. And so it must be transposed. But this equation holds. And so when we wanted to derive the stationary distribution, we solved, in fact, such an equation. And the vector, but we must consider the row vector in order the dimensions holds, or we can make the product of the vector and the probability matrix. But in fact, we solve such an equation. But what does it mean? it means that it is equal to the product of the vector times the matrix times the matrix again, because this is nothing than the vector pi. So in fact, it must be satisfied that this is equal to the vector times an arbitrary power of the matrix of transit probabilities. And the same must be satisfied for the continuous time. The stationary distribution is the vector pi which again corresponds to the probabilities of the chain lying in the concrete states 1, 2, 3, and so on in arbitrary time. And it must satisfy that this vector, which is transposed, is equal to the vector, which is transposed, times the probability matrix in arbitrary t. Yeah? So when I recall the idea of the stationary distribution, it must be satisfied that for arbitrary matrix of transit probabilities in the in the case of discrete time, the vector times an arbitrary power of the matrix is equal to the vector. So for all powers of the matrices, this equality is satisfied. And it is generalized in the case of continuous times, so that it is the vector of probabilities such that the vector is equal to the vector multiplied by this matrix of transit probabilities for arbitrary t. We won't calculate the stationary distribution for this case because we would notice something what is quite natural, that the stationary distribution would be equal to the vector 0, 0, 0, 1. And because in the infinite time, we will finish in the state 3. The box will be full sometimes. In some finite time, it must be equal to, it must be full with a positive, with the probability 1. So it makes no sense to show you the stationary distribution in this case. And if you are interested, I will show you some metrics of transit probabilities for which you can find a stationary distribution, which is quite nice. But now I just wanted to show you the usage of transit probabilities for finding the stationary distribution theoretically. So that was the usage which was derived from, or which was the analogy to the usage from the last time, from the last week. And now I will show you something new, what can be done with the matrix of transit probabilities. So now, something new. With respect discrete time. And this new thing are the transit intensities. Here in the matrix, we see the probability of getting from some time, from some state to another state in some time t. And it is in fact the function of the variable t. But we are interested in some actual tendency of the process to go somewhere. And this tendency is nothing than the limit of this function when t is too small. So, when something is too small, it is usually denoted by the letter h instead of t. So, the intensity which is denoted as Q ij is equal to the limit when h is going to 0 of the probability of transit from I to j in the time h over h. The total transit intensity from the state I. This is the transit intensity from the state I to the state j. And the total transit intensity from the state I is Qi, which is the limit for h going to 0 of 1 minus the probability of staying in the state I in the time h over h. Yeah? So, in fact, because it is the limit of this normalized probability, it is, in fact, the tendency of the process to go from the state I to the state j in the unit time, per unit time. So, it means that when the intensity is, for example, equal to 3, it means that if we continue in this trend of this probability, we would skip 3 times from the state I to the state j. Of course, that practically it is not possible, because when we consider, for example, our example with the bulbs, when we jump from the state 1 to the state 2 once, we cannot repeat it. Yeah? So it is not the practical meaning, it is the theoretical meaning. Yeah? When we continue in this way, we would skip 3 times per unit time, per time unit from I to j. Yeah? So, again, we consider some elements with indices I and j, and we are missing the elements on the diagonal of the matrix. So, when we denote Qii minus Qi, we can construct Q, the matrix consisting of the elements Qij, where ij are the states. I won't write it there. Why did we do this step? Look, Qij is the intensity to get from I to j, while Qi is the intensity of the process to go away from I, whenever. So on the diagonal, we would like to have the element with opposite tendency, not with the tendency to go away from the state I, but to stay in the state I. Therefore, this Qii is minus Qi. You will see the meaning when we construct the matrix in our case. So here we will construct the matrix Q, and we can start, for example, with these elements. So Q01 is equal to Q12, which is equal to the limit for h going to 0 of 2h e powered by minus 2h over h, which is equal to h is going to 0, so this term is going to 1, and we obtain the value 2. So in this matrix here, we have the value 2. Let's go to this term. So Q02 is equal to the limit for h going to 0 to h squared e powered by minus 2h over h, which is equal to 1 times 0 times 2, so it is equal to 0. And so on and so on. We can continue. And what happens on the diagonal? And so on the diagonal, except the element with indices 3 and 3, we have the term e powered by minus 2t, and we know that we should calculate Qii as minus Qi. So it means that Q00 is equal to Q11 is equal to Q22 is equal to minus the limit of e powered by minus 2h, over h. And we can use, for example, the L'Hopital rule. So it is minus the limit, the derivative of the numerator is equal to minus 2 e powered by minus 2h over, sorry, my mistake. So 1 minus the probability of staying in the state I. So 1 minus this e powered by minus 2h. So it is minus e powered by minus 2h times minus 2 is the derivative of the numerator, and in the denominator we have the number 1. So it is, this term is equal to 1, so minus 1 times minus 2 is 2. And we have minus here, so the result is minus 2. So we have minus 2, minus 2, minus 2 here. And we calculated that we have 0 here. And when we calculate the remaining limits, and for example here we have the limit of 0 over h, which is equal to 0. And so on and so on, we would obtain such a matrix. And you can see that the property of this matrix is that the sum in each row must be equal to 0, because the sum in the row denotes some stability of the process. When the process, for example, consider the first row, when the process wants 2 times per time unit go from the state 0 to the state 1, and there is no tendency to go to the states 2 and 3 per time unit, then there must be some opposite tendency to this tendency to stay in the state 0. So you can imagine it as the power, the tendency, the power of the process to go from one state to another state. And of course, the power must be, the sum of all these powers must be equal to 0. So this is something new comparing to the processes with discrete time. And how can we use these intensities? So there are many theorems considering these intensities, and maybe the most interesting for us is the following, or I will show you two theorems. Which can be interesting for you. So the first theorem concerning this intensity, transit intensities, is that I will give you the shorter version. The time of staying in the state I has exponential distribution with the parameter qi. And so I skipped all these assumptions. Let's suppose that there exists such an intensity qi which satisfies and so on and so on. Yeah? So the first property, the first usage, maybe I shouldn't call it theorem in this case. Yeah. Because it is too vague to write it in this form. So the properties of transit intensities. The first one is that the time of staying in the state I, so the probability that the process will stay in the state I, 1, 2, 3. I should be more precise. For the time t has exponential distribution with the parameter qi. No. The first version was okay. Yeah, so I'm sorry for that. I was thinking about the number of situations, the number of skips from the state I. So I was thinking about Poisson distribution. I'm sorry for that. Now I'm concentrated. So first, the time of staying of the process in the state I has exponential distribution with the parameter qi. And the second property is when the process leaves the state I, then the probability that it goes to the state J is the ratio of the intensity of going from I to J over the total transit intensity. Huh? So it means that when the process skips from I somewhere, yeah, it leaves the state I, the probability of going to the other state J is the ratio of the transit intensities from I to J and the total transit intensity of the state I. Yeah? So it describes also the ratios of probabilities of going to other states. So that was the practical usage of intensity, or the metrics of intensities for some calculations, which can be interesting for us. And now I will show you probably most known Markov process with continuous time. And this process is called the Poisson process. So still it is the Markov process with discrete states and continuous time. And It is the process describing the number of independent events till the time t. It is usually denoted as nt because, as explained, it describes the number of some events, and when we consider the numbers of situations, we usually use the notation t. T is positive real number, and the definition is that Poisson process and T satisfy the following. First, it has so-called independent increments, which means that when we consider the times t1, which is less than the time t2, which is less or equal to t3, which is less than t4, then the number of events in the time t4 minus the number of events till time 3, and the difference of the events in times t2 and times t1 are independent. And the probability that the number of events in the interval of the length h is equal to 1 is equal to lambda h. Probability that this number of events is equal to 0 is 1 minus lambda h. And the probability that the number of events is less or equal to 2 is. Now I will add something what is maybe known to you or not, and it is the term OH. This OH is such a term satisfying that the limit for h going to 0 is of OH over h is equal to 0. And what does it mean? It means, in fact, that the definition concerns very small time intervals of the length h, where h is going to 0. And it can either happen that there is only one event, one increment, and the probability is approximately lambda, which is the intensity, times the time length, the length of the time interval h, or there is 0 events with such a probability 1 minus lambda h. And we consider only these small time intervals. Maybe the definition which is equivalent to this one, and you can imagine it better, is the following. It is when you imagine some realization. Here we have some discrete time, but our process is the process in continuous time. So it is the process starting in 0, and it calculates the number of events till time t. So it is the process which follows the number of events till some time t. So it means that always when the event which we follow happens, the process will jump. The size of the jump is equal to 1, because only one event happened in the interval. So the process, in fact, is jumping up always when some event occurs. And it means that we can consider the number of jumps in time t, which is in fact the value nt has Poisson distribution with the parameter equal to lambda t. Why? Because we can see that if the probability that one event happens in the time interval of the length h is lambda times h, then it means that in average, lambda events will happen in time unit. And when we consider the number of events, which corresponds to the number of jumps in time t, it must be in average equal to lambda t. And it is the number of independent events, so therefore it has Poisson distribution with this parameter. So this Poisson process is probably the best known example of such Markov processes with discrete states, so it means the Markov chains, and with continuous time. In practice, we can use this process when calculating the number of car accidents when in the case of car insurance, or the number of some, I don't know, high prices, of some peaks in prices in the stock, in the markets. Yeah, that's the basic example from the economy. In fact, always when we consider the independent events, so for example, the number of clients till time t is also the Poisson process, and so on and so on. So it is used for these cases. The second process I want to talk about is so-called Wiener process, and this process has continuous states, so it is never more. It is no more the chain. So it is Wiener process, and this process has continuous states. So still, it has continuous time, and moreover, it has also continuous states. This Wiener process is also known as Brown motion, and this name is more often used in physics or chemistry, but sometimes also when you study some financial literature concerning random processes, you can meet this title, this name, Brown motion, instead of Wiener process. But usually it is called Wiener process, and it is the process with the following properties. First, it has continuous trajectories. What does it mean? It means that it is a random process, but independently on the values, the development can be described by continuous trajectories. The process, which is denoted as WT for T positive real number, this process starts in the value 0. It has, similarly as the Poisson process, the independent increments, and the distribution of the increments, so it means of the differences of the values of the process in time t and s, has normal distribution with 0 mean, and the variance equal to t minus s. It is one definition which you can meet, or sometimes it is written that the variance is equal to the difference of the times sigma square, which is called volatility. This process is very often used in financial mathematics, and it is used as the model of deviations in prices of financial assets and how it can be used. The models are usually very sophisticated, but everything is based on such an idea. An example of the trajectory of the Wiener process is the following. It starts in 0, and then it is quite wild. So the trajectory is continuous, but the behavior is very, very wild. And when we have some model of the price, let's denote the price as the process CT. Then this process CT is equal to some trend plus the drift. Drift plus this process. So for example, the process is equal to some constant costs plus B times T plus the Wiener process. What does it mean? It means that we suppose that there are some initial costs at the beginning. It is the value A. Then we suppose that the process has some linear trend, so it means that the price is, let's say, slightly increasing or decreasing. So the drift of the price is, for example, increasing for B positive. And this is only the optimal situation. But in practice, the price is not so optimal. The price has some deviations from this trend. Sometimes it is higher, sometimes it is below. And these deviations correspond to this Wiener process. So the deviations from this optimal line, given by the initial cost and some increasing drift of the price, the deviations are modeled by the Wiener process. And as I said, this is very, very simple model, which is not used in this form. Usually we use much more sophisticated models to model the prices of the financial assets. But the idea is the following. We're concerning some drift and some tendency of the behavior of the price, and we add the Wiener process to model the deviations. And then it allows us to make some forecast of the prices. So for example, when we are interested of the price being in some bar from this drift, we in fact model only, or we consider only the Wiener process. And we know that the Wiener process and that the increment has normal distribution. So it means that, for example, the probability that the price is between something and something, let's say A plus BT minus something, minus 3 sigma and A plus BT plus 3 sigma, it is, in fact, the probability that a standard normal distribution lies between minus 3 and plus 3. Because, maybe I should write one step more, because it is equal to the probability that the Wiener process the increment of the Wiener process. Now I'm going too fast because of time. But imagine the situation that, therefore I didn't want to write it here. Forget this. So we can transform this task, that the price is in some time between its drift and minus 3 standard deviation and the drift plus 3 sigma deviation, as the probability that a random variable with the variance equal to sigma square, so in time unit, that the deviation that the increments lies between 3 sigma, minus 3 sigma and 3 sigma. And when we make a normalization of this process, it is the probability that the random variable with standard normal distribution lies between minus 3 and plus 3. And it is equal to 0.999 something. Maybe there is one more 9. So it means that when we know the volatility, when we know this parameter, which is in the variance of the increments, we can be sure that our process, modeled by the drift plus this Wiener process, lies between 3 sigma minus and 3 sigma plus, with the probability which is almost equal to 1. This is the method which is called 3 sigma method, and it is very, very often used in the financial mathematics in modeling the prices of financial assets. Suppose that that we can be sure of the behavior thanks to the property of normal distribution of the increments. So I'm sorry that I was so fast at the end, but we must finish. And I just wanted to give you some overview of practical usage of the random processes, which we were talking about in the last 2 lectures. Okay, so this is the end of the whole lecture. And if you have any questions, we can solve them through the exercises. Thank you for your attention.